we can start now. So before you start, let me allow you to introduce to my participants.
Okay, thank you so much.
Yeah. So today we have Dr. Samiru from Sri Lanka. He is a senior lecturer in the Department of Electronics and Communication at the University of Moratuwa, Sri Lanka.
Yeah.
And he is having very good academics, BSc and MPhil degree from the Electronics and Communication Engineering department from again University of Moratuwa, Sri Lanka. Electrical and Electronics Engineering, PhD in Electrical and Electronics Engineering from University of Melbourne, Australia. And also he is very good in research, and his research includes integrated sensing and communications, satellite communications, signal processing for wireless communication, and he is holding several reputed publications in terms of conference and journals. And his today's presentation, as shown in this slide, is based on machine learning for next generation wireless network. So the session is going to be very informative as well as innovative, enjoyable for you. And once again, I would like to express my sincere thank to you for accepting our invitation. Thank you very much, Dr. Samiru. The stage is all yours.
Okay, thank you so much for Dr. Rohit as well for that introduction and giving me this opportunity as well to address all. And yes, as he mentioned, I'm from University of Moratuwa, Sri Lanka, and I did my PhD at University of Melbourne in wireless communications. So today my talk will be based on applying machine learning to these wireless communication setups, which is one of the popular areas in research these days. But yet there are a lot of opportunities for us to apply machine learning into wireless communication systems, because there are a lot of challenges at the moment in this domain. So you can see that in my presentation, I have...
Sorry to interrupt. Before you start, can we have a request to record this session with your permission?
Yeah, definitely.
Yeah. Thank you very much. Please go ahead.
Yeah. Okay, I hope you all can hear me clearly. I am in a little bit dark background, so that's why my face is not clear. So that's why I turned off the camera. But I hope you all can hear me clearly. Now,
the voice is clear. Your presentation is also visible to us.
Is it clear?
Yeah. It is clearly visible. Your voice is also.
Okay, great. All good. So we'll start now. My title says it's machine learning for next generation wireless networks. Now, there are two key things here: machine learning, which is very popular these days, and wireless networks, and especially next generation wireless networks, which we talk about 5G and beyond, especially targeting 6G. So in this talk, my main focus would be to introduce how we can apply machine learning to wireless communication setups and discuss some of the cases where we can study even now. For example, there are a lot of areas where we can think that we can apply machine learning, but it's sometimes very difficult to do that because of some of the challenges that produces by wireless networks. But here we can, in general, not in very deep details with theoretical understanding, but we can simply look at where we can apply machine learning into regular wireless communication setups. That's the main purpose. Now, before that, I know that almost all of you are familiar with machine learning, but I thought of just giving some introduction to machine learning, especially supervised learning algorithms, because we can see that most of our machine learning related communication related problems can be addressed simply using simple machine learning techniques. So that's the way forward, as I think. So therefore I'll take 15-20 minutes of this presentation time just to introduce or refresh your memory on machine learning. One key thing is that we all think that machine learning is a black box, and we might sometimes people say that we can't understand what's going on inside that, but I think when we apply machine learning kind of ideas to wireless communication setups, we must need some understanding of what's happening inside. Otherwise, it will be very difficult to apply machine learning into wireless communication setups. So that's why I thought of giving it in that perspective, some theoretical background, and how we can adjust or apply these machine learning techniques into wireless communication setups. Okay, now we all know that when it comes to machine learning, there are few keywords going here and there. So one is this artificial intelligence, the other one is machine learning, the other one is deep learning. Sometimes we think that they all are similar and we can interchangeably use, but there are unique identities for these keywords as well. As an example, if you think that what is artificial intelligence or AI involves anything that you can think of which we can replicate the intelligent behavior. If we can integrate some intelligent behavior into a system, we can say that it has some artificial intelligence. So AI involves building systems that can replicate intelligent behavior. But when it comes to machine learning, there's a one key difference. It's an AI system. That means it has some intelligent behavior, but when it comes to machine learning, we need to bring that intelligent behavior through a method which we call fitting a mathematical model to observe data. So we have a set of data, we try to match or fit a mathematical model to those observed data. So in that sense, you can easily see that artificial intelligence is a bigger set, and inside that we have the subset of machine learning. So we bring the intelligent behavior to a setup using data. So that's why we see that data and fitting a model comes into picture in machine learning models. Now, deep neural network is a type of machine learning model which we all know. So when a deep neural network is fitted to this data, we refer it as deep learning. Now, what's the key difference here? That machine learning is all about fitting a mathematical model to observe data. So if we have a set of data, how we can fit a mathematical model to that set of data is all about machine learning. But we can do that in several different ways. One such way is using deep neural networks. So if when we are doing this process, the process of fitting the model is called deep learning. So you all know that, we all know that it's very famous now that there are three main categories of machine learning: supervised, unsupervised, and reinforcement learning. There are a couple of other things as well, but mainly we look at these three areas. Now, in supervised learning, we have a labeled set of data and we use that to get this intelligent behavior. And in unsupervised learning, we don't have any data, we don't have any labeled data, we use reinforcement learning based on some award or credit behavior. Now, when we depict all the ideas in a summary, as we can summarize all the ideas in this manner. So here we can see that artificial intelligence is the bigger set, then machine learning comes. This machine learning or fitting the data can be done in three main different ways: supervised learning, unsupervised learning, or reinforcement learning. And we'll see that it comes under deep learning later, that all these things we can do in deep learning. That means we need to have more than two hidden layers. That's We'll discuss that in a short while. Okay, now as I said that most of our wireless communication related problems especially can be solved using supervised learning techniques. There are different other techniques also, but most of the problems like detection, channel estimation kind of problems we can solve using supervised learning. So therefore I'll focus a little bit more in this presentation about supervised learning. Now, if we take a supervised learning model, in which method that we follow, we need to find a relationship between the input and the output. That's what we say, that a mathematical model or mathematical equation. So here, mathematical model means nothing else. We try to find an equation, mathematical equation. So here, if we think that our input is represented by variable x and the output is y, what we try to get is a model f, which can replicate the relationship between the input and the output using some parameters phi, some parameters. For example, if I say my input, if I say my input is 1, 2, 3, 4, and my output is 2, 4, 6, and 8, we can easily figure out what's the relationship between these two. Then my output will be 2 times x. So that is what I can say. I can directly say it. And this 2 becomes a parameter now here, input and output. But say that our output is something like this, zero point 0.5 to 6. It is now changed. Now, when we think of a model, we might not be able to get it directly. We might need to do some mathematical analysis to find this parameter. So it's a simple example which you all can understand. What I wanted to say is we can represent a relationship between input set and output set of data by using this mathematical model in general. So that is what we can do. Now we can represent it in this manner. So you have a set of inputs, you have a set of outputs, you can model it like this. This is a mathematical equation, nothing else. Using machine learning, what we do is we find this model. And when we do that, once we found this mathematical model, when we have an unknown out, if we need to find the relationship between the input and output, we can simply do that by using inference. You know that in statistics also we refer to this one. We can use a simple inference to find the answer after that. Now, in a supervised learning technique, if you use supervised learning, there are maybe 5 steps that you need to follow in almost all the cases, even in wireless communications, which we'll see later. Now, we need to train the model. Train the model means we need to find these parameters. These parameters are the things that define the relationship between input and the output. So to make this relationship, we need a set of data. Initially, that set of data we call training data set. We have the training data set in this manner. You can represent using I. What we do is we take the training data set and we have the training output data set, and we can match the relationship using phi. Okay, now when we match the inputs to the output, we need certain objective, because we can't map the input to the output without having an objective. We need to have some objective, and we need to what should be the objective? Now, finding these parameters such that we need to reduce the mismatch between the predicted output and the actual output. That's what we know. So how we can quantify this mismatch is using a loss. So loss quantifies the degree of mismatch of this matching. So when, in that sense, in general, we can say that what we need to do is we have a loss function, which is a function of phi. We need to find the phi values which reduces the loss, entire loss. So that is the phi hat that we find. Once we find these phi values or the parameters, then we have a set of another data which we can use to test the model. So you can test the model by using this one. So this is a well-known procedure, and I believe that you all are familiar with this stuff. But I just wanted to refresh your memory on that one. That's the only reason. Now, if you look at the linear regression problem as an example, this is nothing related to machine learning. This is something that was there for a long time. If you take that one, if we replicate the same exercise here, what we have is we have an input, we have an output. This is a single variable input and output. We have the input output y, and the input is x, which we think that they are related as this one, phi naught plus phi 1 times x, which is something you can add for any other parameters also, but we think that it is a linear system and this is how it related. If that is the case, you can find the loss function by using this mechanism and find the five parameters in this manner. So you come to this mean squared error reduction. Later you'll see that this same thing can be extended to negative log likelihood or cross entropy as well. But this example is nothing related to machine learning. This is just an example where we can justify the method that we just discussed. Okay, there are two different ways in in wireless communication. Both of these mechanisms can be used in our research, but mainly there are two types of models. One is discriminative, the other one is generative models. For example, here we have the output and y. We can build a model which can produce the output directly from the input, or else we can build a model first to replicate the input output relationship, not the output to input output relationship. For example, in wireless communications, we know that this kind of expression we are talking about, I'll come to this point later also. This is the received signal, transmitted symbol, and the channel and noise. So we can build the model to when we give the y, we get x, or else we can train it when we give x, we get y, and then come back to this one as a next step like this. So there are two different ways which we can understand easily. So we have here input output relationship. This is the one that is very famous. That's the one that we use a lot. We can directly get the output from the model. But generative models does it other way. We build the model to replicate the input to the output. Then when we need to find the output, what we need to get, we need to find GMUS function. So these both the methods are okay. But the famous, mostly useful one is this in modern day communications or modern day systems. Okay. Now we can simply divide these problems that come under supervised learning into four main categories: regression, multivariate regression, binary classification, and multi-class classification. Now, we can think of each wireless communication related problems under each of these categories simply. We'll see that later, but we can see that what is regression, the model returns a continuous number. If I need to predict a continuous number as the output, then I should go for a regression model, and it's a regression problem. On the other hand, it can be a multivariate regression problem if I need to predict more than one output variables which are continuous. For example, here regression problem, if I need to predict the temperature values depending on the year or something like that, then you have a regression problem. You are predicting a continuous variable, and multivariate means you predict the maybe temperature and carbon dioxide level, both, something like that. So binary classification means the model attempts to get an yes or no type of answer. That means you try to classify into two categories. If you input a picture to the model, the model says whether it's a cat or not. Or else if we give an answer, it says right or wrong. Like that, it's only a binary classification. For example, if we take a BPSK kind of setup, you transmit a single bit at a time, then you need to decide whether it is 1 or 0. So if you ask the model whether it is 0 or not, then you will automatically can get the estimated bit by using that answer, that kind of a thing. Multi-class classification, this is the most important one in detection problems in wireless communication, where we are trying to categorize into multiple different classes. The model assigns the input to one more than two classes. So, for example, if we transmit a QPSK symbol and if we ask the machine learning model to predict which symbol has been transmitted, then you have four options to select. So therefore, it's a simple multi-class classification problem. If we train the problem according to a supervised learning model, we'll see that those examples later. But these are the four main categories that come under supervised learning. But that's one thing, that one important thing, even in related to wireless communication, is that how we input these details, or how we input our real world input, or encode, how we can encode the real world input before giving it to the model. For example, there's a real world input. As an example, this in communications, maybe this symbol that we send, maybe a QPSK symbol. It is, I don't know, for some reason I can't write it in a proper manner here. It can be this symbol. So how I can't give it into the model as like this. I need certain type of encoding. Maybe if I use one hot encoding, because I have a real part and imaginary part, I may give the real and imaginary part separately. I may, because there are four options. I need to, if I use one hot encoding, maybe this may be the one that I'm giving as the input. So this is called encoding. This encoding is so important in wireless communication problems. This is encode. If we can try with different types of encoding and different ways of encoding, but it's something that's pretty useful to investigate. So anyway, in general, you need to find a way to encode the input data as a proper way to the model. Then model predicts something. Model predicts something. So, for example, let's say it predicts this symbol itself. This is the these are the four symbols. So I am transmitting this one. So if the model predicts it correctly, maybe the output may be 1 0 0 0. So it says that then the real world input is actually 1 plus j, this one. So you can see that this is the decoding part. That means the output is this one, the real world output is different. So this mapping is important. We'll see an example later there where how we can apply this into a communication setup. But this whole encoding and decoding, and how we can encode the input and how we can decode it at the end, will be important in normal supervised learning problems. Okay. So before a little bit of history here, before we come to these deep neural networks, what we had was these shallow neural networks, where we had only one hidden layer, shallow neural networks. Now, deep neural networks means you need to have at least two hidden layers. We normally have more than two hidden layers in deep neural networks. Now, here, shallow neural networks are important in two aspects. One is we can understand what happens inside the neural network by looking at these shallow neural networks. That's one of the important and pretty useful thing. We can see what happens here mathematically, because we have a lesser number of hidden layers, and we can feel what happens there. Now, as an example here, you can see we have a shallow neural network where we have one hidden layer with three hidden units, which I have indicated using H1, H2, and H3. Input is X, output is Y. Okay, how we can model what's the basic principle behind all these when we represent it using a neural network is that you get the input, you weight it by a coefficient and add the bias, add the number. Like it means like in when we learn about basic maths, we know that this y equals m times x plus c type of equations. So this is a line. Actually, all these hidden units, before activating it, we have something like this, these lines. So in higher dimension, we can think of it as a hyperplane. But in this example, where we look at the single variable case, we have these lines. But in higher order, it's hyperplanes. Uh, Now, what happens here? We have something here, H1. Those are called hidden units. Now, each hidden unit, we have an activation function A. Activation function. Inside that activation, the parameter that we pass to the hidden layer is this input multiplied by this weight and add the bias. That's what we have done here. So it's something like that we feed into the activation function. Now these are linear functions. So if we use linear functions to predict something like this, we can never predict this sine kind of curve using a linear function. We can't. It's in this case it's a line, so we can't do that. We can predict this kind of a thing using maybe piecewise linear functions. Like as an example, something like this, if we use a piecewise linear function, we can do that. To achieve this piecewise linear nature, we need an activation function which is a non-linear function. So non-linear function. What is the most popular nonlinear function which we can use these days is this ReLU function. There are so many other nonlinear functions, but for the convenience of presenting here, I have used the ReLU function. ReLU is that simply if your input is positive, it gives that as the input, and if it is negative, it returns zero. So this is the ReLU function. Now, what will happen? We need to get a piecewise linear model to predict a nonlinear function like this. If I need to do that, you can see that I need to bend this line from here. I can achieve this bending using this ReLU function. That's why we use this ReLU as the activation function. So in terminology terms, this before the parameter that we input to the activation function, we call the pre-activations, and the output of this output after the activation function, we call the activations. So HD is the activation. So at the output, you again weight the activations in the same manner. So this is the final version of that one. So you have the y, which is phi 1 times h1 plus, like that you'll get it at output. Okay, so this whole function produces a piecewise linear model. We'll see it as an example in this diagram. Now this is the input to the hidden unit. So we have three paths. So in each path we get a linear function, which we can represent like this, a linear function. Now this linear function will undergo this activation function. So therefore, what will happen? So at this point, it will at these points it will be broken like this. So this side, since when it goes beyond zero, it returns zero. So this is the activations. These are the activations. Now these activations will be added at the will be multiplied by another weight before adding them. So you'll add that one. So this one may be shifted in any direction. So in this example, it has shifted here. So it was here, there. Now it has shifted somewhere here by multiplying. The slope will be different now. And finally, you add all. Now you can see that we have this type of a curve. So it's a non-linear one. It's a piecewise linear overall. So this is a linear up to here, linear up to here, linear up to here. It's a piecewise linear function. In this example is in single variable, a single it's one dimensional case. Therefore, we can represent all these things using lines. Now, this output we can use for two different things. We what we had was we had four different problems, but two categories: regression or classification. Now, if I use this as a regression problem, maybe I might predicting something like this. I might use it to predict a relationship like that, so it may be predicted in this manner. Or else I can use the same thing for classification. If it is binary classification, maybe I can think that in this region the answer is yes, in this region maybe answer is no, or one or zero. Or if it is multi-class classification, maybe I can have different thresholds. In those thresholds I can use this one. So you can see that once we develop this method, the output I can interpret according to my requirement, whether it is a regression problem or a classification problem. So in what's the usefulness of this the usefulness of this simple example is that we can see what's going on inside this simple model. That means we can see how the lines are bending, how we make the piecewise linear model to fit into a curve or a classification problem. So that's something useful. But when we increase the number of inputs, or when we increase the dimensionality, it is tough. What happens is it goes beyond our visualization capabilities. Like for example, if we say 4D, 5D, 6D, then we can't graphically show it, but we can even have a feeling, like we can extend our understanding on 3D up to 3 dimension to those up higher end as well, higher dimensionality as well. So therefore this folding and bending kind of behavior will be there as well. So it comes to a polytope. So it's like if you get a piece of paper and if you bend it here and there, you'll ultimately get a shape like a convex polytope type shape. So when there are more than two inputs to the model, it becomes difficult to visualize. So our interpretation is similar. So the output will be continuous piecewise linear function, and it will be like convex polytope. Okay. So this is what we had in early. So I think I explained this terminology. But what we are interested in now is that deep neural networks, where we talk about deep neural networks a lot. What the deep neural network is? It's an extension of the shallow neural networks, where we have more than two hidden layers. So we must have more than two hidden layers, two or more than two. So it's the concept is same. You add the weighted inputs and add a bias, and then you pass it through an activation function. That's the normal path. So ultimately you get something this one. Now this part is very similar to shallow neural networks. Now we have something called hyperparameters. Now we have a set of parameters here. You can see that this beta, omega, they all are parameters of the model. So we call them parameters. But there are other set of parameters which are not directly involved with the model, but they contribute to the success of the model. So what are them? We call them hyperparameters. For example, the width and the depth of the model. So width means the number of hidden units in each layer, this way. So the depth is the number of hidden layers, how many hidden layers. So those kind of things. So for example, you may have a problem, you might need to now decide what's the width and the depth. There's no straightforward way to do that. You need to do it, test it, and come up with the best approach. So the total number of hidden units is a measure of the capacity of the network, how good it can perform. It's a measure of that one. If it is too good, then it will be difficult to generalize your ideas to normal problems. So therefore, that's an optimum manner that you can find these capacities and all these things. Okay, now what we discussed was actually the very fundamental things on machine learning, and we what we thought was we can directly predict the input, predict the output from the inputs. But this is not what happens in most of machine learning algorithms models today, because it is difficult to do that, and it is not easy to do that as well, because we are dealing with data. What we actually do is we use probability to achieve this goal. So there's a shift in perspective uh, than what we discussed. The concept is similar, but what we do is a little bit different. So we consider the model. What in machine learning we build a model, but what how we build that is that we consider the model as computing a conditional probability distribution. This is the conditional probability distribution that we consider probability of y, the output given in the input, or possible outputs given the input. So we try to, instead of directly predicting the output, what we try is now to build this conditional probability distribution using a machine learning model. Okay, the loss encourages each training output yi to have a high probability under the distribution probability of yi given xi computed from corresponding input xi. So that is what we are going to do. So we train the model so that we get a higher probability for this one, not something else. We try to reduce the probability for this one. If we give another one, maybe a j, it should be go down, but this one should be higher. That's how we train the model. So the question now is, we know if we have input output directly, and if we need to train to find the output, we know how to do that. But question is now how the model, this f, can be adapted to compute a probability distribution. That's the question. So what we do is we choose a parametric distribution. So we know that this is a probability distribution. We choose a parametric distribution, which we can represent using probability of y given theta defined on the output domain. I'll give an example later. It will be more easily understandable then. But what we do is, instead of directly predicting this one, we find a parametric distribution and we use the network to compute one or more parameters of that. Okay, what this means is, for example, the model can compute different distribution parameters theta I according to this. So we are not now you can see the difference here. We are not going to predict yi directly. Instead of that one, we predict theta I, something a parameter which is related to theta I. Earlier we directly predicted yi. That is not what we are doing now. Instead of that, we predict a parameter theta which is related to yi. So in this case, earlier we tried to do the same thing. We tried to find the parameter so that it maximizes this conditional probability, and we can replace it with theta I. It is same. This is how we have the parameter theta I. We need to make sure that theta I has these properties. Then we can model it in this manner. Okay, I'll give an example. We assume that independent and identical distributed samples, because otherwise we can't do this. This step won't be there if it is otherwise. Okay. Now this whole loss function can be expressed in a different manner, because now we can see that what we have here is a probability value which is in between 0 and 1, a value between 0 and 1. We have how there are thousands of samples, so maybe I goes from, let's say, 100,000, maybe 100,000 sometimes, so let's say even 1,000. What happens is that this number is very small. It's between 0 and 1. When you multiply thousand times, like several values, what happens? The resultant value is very small. It's very small, which is very difficult to deal with in a computer. So therefore, what we do to expand it, we use log. Log is a monotonically increasing function. So therefore, this output of the argmax, it won't change. It's if because of this condition. So if z is larger than z prime, that means log z also greater than log z prime. So therefore, this is correct. But what's the advantage? Now we have a probability value, and it comes down to a summation. So if the probability values are in between 0 and 1, when you add them 1,000 times, it's larger. It's a value with the larger than it may be a larger value than 0 and 1 anyway. So therefore, it's easy to handle. So that's the convenience of using log likelihood function. Now, normally we are more familiar with minimizing some, because we are talking about a loss function. We need to minimize it on convention. So that to facilitate that part, what we have used is negative log likelihood. So you have a negative part, and this argmax become argmin because of that. So therefore, this is the normal. The very famous negative log likelihood function. So this is how it comes, and later you'll see that it's the same thing as cross entropy as well. Okay. Now, we haven't yet predicted the output yet. What we did was we predicted a parameter which is related to the output. How we get the output is using inference. Using inference, what you do is you try to maximize this probability and get the output value. We need a single value. We need a value to the output. How we get the output is by using this probability distribution is like this. We find the y value which maximizes this probability. Okay, if we look at an example, this is very clear. Now, for example, if we will start with simplest case, let's assume that the output is y. Y is in 1D, so it's a real number y. Input is x, and the model is this. Now this, what we need to do is we need to find a model y. The output is y. It's a real number. So we need a probability distribution that can replicate that behavior. What's the most frequently used probability distribution to replicate this type of thing is this univariate normal distribution or Gaussian distribution. We can use this. Now, what we do is we know that for a normal distribution, there are two parameters, mu and sigma. What we try to do is we can think that variance, we can keep aside variance for the moment. We can try to predict mu using machine learning model, because we said that we need to choose a probability distribution and we need to predict one or more parameters of that probability distribution using our machine learning model. That's what we are doing now. So we choose univariate normal as the probability distribution of y, and now we need to predict either mu, sigma, or both together. So in this example, we'll predict only mu. Okay. So if that is the case, we can use the model to predict mu. So the model actually does not predicting y directly. Instead of that, it predicts the mu. Once we have the model, so we know that this is the probability distribution. So this part comes by mu, and you can simply substitute that one and find the loss function, and it comes down to this expression. And finally, once all done, we'll have a set of parameters. Now, by using that parameters, we need to find y, because we have found mu, but we need to come back to y. That's our objective. We don't need mu actually. What we need is y. How we find y? We need to maximize this probability. at which time this probability is maximized will be at mu. So therefore, our in this case, if you use univariate mu, because we this probability is maximizing at which point it's mu, because we know that it's a normal distribution, it comes at mu. So therefore, we can directly say that y hat, the predicted output, will be equivalent to the model output. So that's a indirect relationship. So that is how we use this univariate regression model. So in binary classification, what can we do? So simply binary classification, now output is either 1 or 0, something like this, 0, 1. It's a label. Now to predict something like that, what we can use is a Bernoulli distribution. So it says 0, 1 Bernoulli distribution. So what's the probability of that? Is this one: when the output is 0, you have 1 minus lambda. This probability equals lambda when y is equal to 1. So what's the parameter that we can predict using the machine learning model? Is this lambda. So we can predict it lambda using the machine learning model. We train the machine learning model to do that. So what can we do that? Actually, this logistic sigmoid comes into play in this binary classification problem, where you can simply do this. Okay. So I'm going to go deep into these things, because I think you all are familiar with this, and the time is also a constraint. So you can use logistics sigmoid function to do these whole things. So this binary cross entropy loss, it's same thing that as I mentioned earlier. Okay, so in the multi-class classification, this is so important when we discuss about detection in wireless communication setups. So in multi-class classification, we use a categorical distribution to model the output, because we have k number of categories. We have categorical distribution with the parameters lambda 1, lambda 2, and lambda k, and we can use softmax as the function, and this comes as output. Okay, I wanted to say something now. Softmax comes why? Because this we are giving a probability, so that probability should be in between 0 and 1. Even logistic sigmoid also for the same purpose, because the model, the machine learning model, can predict any value in the real axis, but we need a probability value. So how to convert that value into a probability value is done by the softmax function. Yeah. Okay. So you can see that this multi-class one comes. Yeah. There are non-probabilistic approaches also, like support vector machines and AdaBoost, because what we discussed was based on probability. We tried to apply a probability distribution function and estimate something, and through that model the parameters. But there are SVM and AdaBoost, which is non-probabilistic methods. Okay, now we have some understanding or refreshing memory about machine learning, because these concepts we need when it comes to wireless communication setups. Okay, if you look at the digital communication setup, digital communication setup means inside from the source to the channel, the modulator, there's a digital interface. That means it passes, bit stream goes inside. That means if we have a source, for example, it can be my voice, or it can be a text message, ABC kind of thing, or something like that. So this source produces some information. So it's if it is my voice, then it's an analog waveform, or else a discrete wave signal like ABC. If you type, or if you use maybe WhatsApp or something like that, you type. So therefore, it's a set of bits. Now, because it's a digital communication setup, the first thing that you need to do is you need to convert the signal into a common manner using ones and zeros. So that is what happens inside the source encoder. So source encoder convert your analog signal or the discrete signal into a set of ones and zeros. So after this one, you'll see a set of ones and zeros passing in the stream. So you need to do it in a more efficient manner. You need to use the least amount of bits to encode this information that is coming. So we have these Hoffman codes and all these things, and it comes discrete, and You need this. If it is an analog waveform, then you need to do this sampling, quantizing, and encoding in an efficient manner to represent these signals as ones and zeros. So that is source encode. So source encoder simply does is that you convert your signal into a set of ones and zeros. Then in the communication chain, we have these channel encoder. What channel encoder does is that you'll add some redundancy for error correction purpose, because when we transmit a set of bits to the receiver destination, it is very difficult to figure out whether it has been received correctly or not. Therefore, we need a certain mechanism to check, at least, if not, if we can't correct, at least to check whether there's an error or not in the data link layer. So how we can do that? We can add a redundancy bits, like using parity bits or CRC, cyclic redundancy check, or some mechanisms we need to add that comes under channel encoding. Then we have the modulator. Now we have a set of bits. Up to this point, we have a now set of bits. Now, how we can transform these set of bits into a waveform again? Because in the channel, we can't send ones and zeros. We need to convert it to analog waveform again to transmit. So therefore, that part is handled by the modulator. Actually, people sometimes divide whole modulator into two sections, like bit mapping and, for example, this modulation schemes, QPSK, QAM, or any something like that, and then up conversion phase separately. In this picture, I assume that both are together, like up conversion and the modulation of bit mapping part, or pulse shaping, and everything under modulator in this picture. There's few things going on, like in phase and quadrature component division and all these things. I assume that goes under that one in this picture. Then the channel is AR, because we are considering wireless communication setup. If it is wired, definitely the wire or optical cable or something like that. Then the reverse path starts, the demodulator. You try to decode it back. That means you get an analog signal. From the analog signal, you try to get it ones and zeros. Then you have the channel encoder, decoder to check whether it is correctly received or not, and whether you need to discard the packet or not. Then you have the source decoder, and ultimately you hear the what. If it is a voice signal, you hear the voice. So this is the communication chain. There are several things that are happening here. For example, there are, in this case, before transmitting, there are multiple things that you need to convert it from digital to analog domain. Then you need to pre-code the signal. There are several things happen, but for simplicity, we have not included all the details. In this side also, you need to combine the signals, because you'll receive, maybe your receiver is a multi antenna setup. You need to combine the signals that are coming in different parts to different antennas, then combine them, then take the decisions and all these things, synchronization and many other things going on. But this is the simple picture that we can show. Now, by looking at this picture, we can figure out there are a lot of places where we can apply machine learning. For example, now this source encoding, how we can think of a source encoding in terms of machine learning. Now, I'm not going to discuss about source encoding as an example in this talk. That's why I take this here. So you can see that when we have a signal, some few things maybe we can see, we can check. We can build a model that can generate the set of bits like these ones and zeros if we give the input as the source or sample. I don't know how it is efficient, because it's something smoothly running at these days with the known techniques. So therefore, maybe people have not investigated that much for that source coding domain, but something that we can do. What people are actually interested in this jointly doing this one, source and channel encoding both. If we can achieve that part together, that's an advantage. So therefore, people have investigated in applying machine learning here. Why I say that supervised learning is pretty important in these cases is that in a wireless communication setup, most of the time we have this input output relationship, and we can train it, at least offline we can train. So that's an advantage for us. So that's why supervised learning comes into play a lot, because we need a very simple method to do all these things, because we have a limited time amount, so therefore it's a must. Okay, the other thing is modulation and demodulation part. That means detection problems can come. Then demodulation, that channel decoding part can be there. So there are a lot of places where we can apply machine learning by simply looking at it. Now, before applying machine learning to a set of common problems, but we'll see in general, we have these. If we talk about point to point communication, so in this case I just focus on point to point communications, but obviously we can extend the same ideas to multi-user communication or point to multi-point communications as well, because here what I am considering is point to point communication. You can extend the ideas to multi-user. That means if you have multiple users and a receiver, we can simply extend. This is the size of model: single input, single output, single input, multiple output, single output, multiple input, multiple output. So we can, what we have is normally the simplest model that we can apply machine learning and see how it works is this single input, single output case. It's important because we can apply machine learning, and we have the analytical solutions to most of size related cases. So therefore we can analyze the setup. So always we start as researchers applying machine learning models to size of case. We know the result analytically, and we wanted to get some insights using machine learning also, then we can do that using size model. But the pretty useful case comes actually when we have more than one transmitters receivers or MIMO kind of setups, because the problems come in MIMO setups a lot compared to all the other size setups. Okay, we'll discuss that. But now, if we think in the modeling terms, what we have at the moment is, if we think it's a discrete memoryless channel, we all know that we can simply represent the low pass equivalent or the baseband equivalent model as this one. Y is the received signal, H is the channel, X is the transmitted symbol, and N is the noise that has been added at the receiver. So this is the receiver noise, which we normally assume that it is Gaussian noise, additive white Gaussian noise, distributed as this one. Maybe channel also, to simplify the analysis, you can assume Gaussian channels, but there are other cases as well. So X is the transmitted symbol, like QPSK symbols, CRAM signals, or in general Gaussian transmitted symbol. So this is a single input, single output case. You can extend the same idea to single input, single output, multiple input, multiple output cases as well. And ultimately, multiple input MIMO setup looks like this. Okay, what we need here is that we try to use this equation to get some understanding using we will try to, with this equation, what we normally do is we can predict X. That is what we call, if we know Y, we can predict X. That is what we call detection. We all know that. If we know X, and Y both, we can predict H as well. That is channel estimation. So you can see that by looking at this equation, simply if you have a set of data which can act as input and the output, we can use a machine learning model to predict the channel H or estimate X. So therefore, by looking at this equation itself, we can see that we can apply simple machine learning models for detection problems and channel estimation, definitely. So by looking at this problem. There are other cases as well, but that is something that we can easily understand. So here we are going to apply machine learning into detection. If we try to do that, but what's detection now? Simply what happens, in a normal scenario, when we use mathematics to find this output, what we do is, if we assume a scenario where we assume that QPSK symbols, QPSK, so we transmitted either one of these x naught, x1, x2, or x3. There are four symbols we transmit. So our received signal y, so this is a size of case, h times x plus n. So size in y is y has a relationship like this. So y is a function of x. Y is a function of x. We need, what we do want to do is, we need to find this find the best value of x so that it matches y. Now, if we look at this one, what has happened in this case, if we assume that we know channel or coherent detection, the channel rotates any of these symbols, whatever the symbol that we transmitted, it will be rotated by the channel. So the channel, when we rotate it by the channel, it comes down to these places. So our received signal lies here. The gut feeling says, if I need to choose a symbol, uh, by looking at all this information, I need to pick the closest symbol to this received signal. So that is this one. So X naught. I'll pick X naught as the symbol, transmitted symbol, estimated symbol. So this is the detection. Actually, this is the detect as well. So you get the minimum norm distance, Euclidean distance, 1 as the detector. So can we do this kind of a thing using machine learning? If we do it in that manner, what we can do? So if we have a set of data, say that if we have a set of data x, and if we have a set of y, if we know the relationship, the machine learning model should be able to find this relationship. It's relationship. So it's something doable from our gut feeling. We can see that if we have x and y, we can train it so that it can figure out this relationship with certain accuracy. People have done that. But this kind of a technique works mostly in low SNR regime. When it goes to high SNR regime, it fails. Machine learning fails because this noise does not have a greater effect in high SNR domain. What machine learning models are good at learning this kind of noise behavior, it can learn. Like if you have something relationship, what we do here is we have hx, around that we have a noise. But this, when we have a high power region, this noise effect is compared to the power received power is low. So therefore, that means SNR is high. That's why. So therefore, machine learning models fails. You will see that when we apply this kind of a machine learning model, simple softmax or simple algorithm, when we fit into this kind of a problem, it's a classification problem because you need to pick 1 out of 4. So you'll see that it works well in low SNR regime. Okay. Now, if we try to actually apply machine learning into a communication setup, we can think of a framework. This is from one of the papers. I think I have listed down that paper as well. So this is a framework that we can use. Now, in usual scenario, we transmit data and we send a set of pilot symbols beforehand to get the channel information. So you can coherently detect it at the receiver. So this period where we assume that channel is constant or channel is same is what we call coherent time. So this coherent time is a very small time period. So in that period, you need to do that. Normally, if you take maybe frame size, you need to transmit as data maybe 12,000, 13,000 bits as the data, and we need to use a portion of that frame as the pilot symbol as well. So this frame actually begins with the preamble and you transmit. But let's say this whole area, maybe For our convenience, let's assume it's about 10,000 bits for the moment. So you need to use a portion, maybe 1,000 as the pilot, and you need to use that 1,000 bits to train the model. Now early days we use pilots, now we have to use it as training. So you do training to find the channel model or whatever, some training going on with the machine learning. So that part we can utilize. This is the connection between this one. Earlier we had pilots, now we have a training duration. So this is the process that follows. So you have this digital to analog converter, then you have this analog recorder if you use a hybrid one, then analog combining and ADCs. This is not the fully digital one. If you have full digital setup, you don't have these two. Apart from that, others are same. But anyway, the key idea is that we can replace the pilots with now training. When we do that, at the receiver, there are two ways that you can address the problem with machine learning. In traditional way, you estimate the channel, you use that estimated channel to coherently detect the symbol. When you use machine learning, there are two different ways that we can use machine learning. One is model based and the other one is model free. Now in model based one, if we know something about the channel, we can feed that to the model. For example, if we think that if we know the channel at the receiver, we can feed the channel into the setup. If we know the noise distribution at the setup, we can feed that into the model. If we know that there are some non-linearity associated with the ADC, we can feed those information into the model in model driven, so that you can increase the accuracy. But that is something called the physics based machine learning, also come under model based one. That means we give whatever we know. In model free, we don't give such thing. We just give the input and the output, x and y, and model should figure out what happens there. That means we give input and output. It needs to figure out the channel, it needs to figure out the noise and everything. So that's the model free one. Okay. Now this kind of a model, this kind of a machine learning model is so it does a useful thing when we have some imperfections at the receiver. When there are no imperfections like IQ imbalance or synchronization problems, when there are nothing like that, our mathematical model may work better. So we know that all the mathematical models, we have defined them. We know maximum likelihood detectors in some of the cases, so we can use them for detection. But say that we have these synchronization problems, IQ imbalance, imperfections, noise distributions are varying, some kind of imperfections, then we can use machine learning algorithms to do the stuff, because we don't need to mathematically model. We can use a model free kind of algorithm method, and we can allow the system to detect these errors, and it's kind of normalizing these errors and finding the best result. Okay, in my perspective, that's where the machine learning will be more useful to be applied in detection problems or at the receiver. But if we can use the machine learning to detect the channel, but estimate the channel or else detect the symbols. I think when there are these problems, machine learning will be a very useful thing. But if the conditions are ideal, then it can be done using our ML detectors. Also, if we don't know the ML detector, if we are working with suboptimal one, maybe machine learning may produce a better results as well. There are a lot to research on this topic as well. Okay, so this is an example. There's a paper also that has been done. So the challenge, there are goods and bads in anything. So these are the goods and bads of these two techniques as well. Okay, if you use this, we can use the for channel encoding and decoding as well. I'm not going to explain all things, but I just wanted to highlight that we can do something like this with machine learning. So here we have used the machine learning to achieve channel encoding and decoding. So we have an encoder and a decoder architecture where we do this encoding and decoding in this manner. Okay. So channel estimation, as I mentioned, you can use the training period, and we can observe the data, and by using that one we can estimate it and we can use it. That's what we can do. Now this is something very popular these days, this end-to-end learning system, end-to-end learning. Now that is something interesting actually. People are working on this one, this a lot, because if this is going to be if this is a success story, then there are a lot of advantages that we can get from that, but it is still in primary level. What we do here is that when we need in classical communication, when we need to transmit a symbol, we need to do all the modulation, we need to do modulation, and we need to transmit it through a channel, then we need to demodulate it, and then we need to get it back. But here, these modulation and demodulation schemes are fixed under certain ideal characteristics. For example, we know that what's the capacity maximizing transmit symbol distribution under Gaussian noise. We know that it's a Gaussian distributed, the symbols are maximizing the capacity. But these ideal conditions, when there are no such ideal conditions, maybe channel may be pretty different. A dynamic channel, it may be have different conditions to ideal ones, which we think that compared to these Gaussian channels. In those cases, maybe this ideal or optimum distribution of the transmit symbol may be different. Maybe in these cases, we transmit a symbol stream like this. Maybe under this case, maybe this kind of a symbol distribution may be ideal. We don't know. But using machine learning, what we try to do is we try to over as a whole setup, we try to optimize. We try to get the maximum data rate, or less. We reduce the symbol error probability or something. Some under some objective, we try to plan the transmitter side and the receiver side under given channel. So this is the autoencoder type setups, where we just give the data symbols, a set of ones and zeros we present. The machine learning model will decide which modulation scheme. We don't know what's happening actually. We in a certain manner, it is not the same modulation schemes that we use, but it will be different. Constellation diagrams will be different, and it passes through the channel and it gives some results. So that is another idea that people are working on. So this auto encoder based end-to-end communication setups. A lot of results are there, but still a lot to go. Lot of things to be improved. Initial ideas are there. The other problem is in a multi-user setup, maybe resource allocation, because we know that to optimize the capacity, data rates, achievable rates, we can, in an efficient manner, you can allocate the power for each transmitters, receivers side. That's one other thing. Even this ADC non-linearities, under those kind of conditions also we can allocate power according to certain cases. So this is a k-user setup. We have interferences to reduce certain things, how we can optimally, because these resource allocation problems are most of the time optimization problems. It comes down to sometimes non-convex, under non-convex optimization functions, and it is difficult to do that. We can search, we can look at whether we have a different way to address this problem. Can we use machine learning to do this thing? So that is another area of interest. Okay. So there are a lot of challenges. There are places where you can apply machine learning in communication setup, but a lot of challenges. So large training overhead is the main problem, because we have a small amount of time as the coherent interval. We have to use that portion of the coherent interval. If you do online training, maybe we can do offline training and do some probabilistic methods to get some advantage and to reduce the training overhead. That's something to be investigated. Then enabling deep learning based frameworks in frequency selective channels, especially like If the channel is not flat fading, it will be difficult to handle. So therefore, it's another area. Then deep learning in time varying channels and deep learning in synchronization when there's offsets in synchronization and beam designing. On the other hand, a lot of new technologies are coming up. Can we use machine learning in reflective intelligent surfaces like RISs or integrated sensing and communication domains? So there are a lot of things that we can plug these machine learning ideas. But from my side, I think from the research that we are conducting here, what we got to know is that we need to understand the basic idea of what's happening when we apply the machine learning technique. When we apply machine learning technique to a simple problem like size or setup, it is also difficult sometimes. At some points, it becomes really difficult to get the accuracy levels that we need. So therefore, we need to understand where the drawback is, what happens, and all these things. We need to give the solutions for them as well. So therefore, it's not a smooth thing. Like even though we say that we can simply apply machine learning, it doesn't work like that. If you have input data set and output data set, and if you feed it to a common machine learning method algorithm, it doesn't produce the results that we need. So therefore, a lot of analysis has to be done as well. So optimizing and how we can produce the best result using a machine learning problem is still a problem to be solved. I think the framework also we need to think on in terms of that as well. Okay, so with that, I conclude my presentation. I hope it's very simple on one hand. What I wanted to do is just see where we can apply machine learning in a wireless communication setup. We all can work on these problems and produce results, and ultimately we can see where we can head using machine learning in the domain of wireless communications, because we all need to work on these problems so that it gets advanced results. So that's the only purpose of doing this lecture. Okay, thank you so much for listening. And if there are any questions, we can, I think we have about 10 minutes. We can discuss them.
The session is now open for any question if you have. Also, the participants are requested to remain connected since we are having a validity after a few minutes as soon as this session is concluded. So the room is open for any question or any query. You can also put your queries in the chat box also if if your mic is not working. So I think there is no query because most of the slides were self-explanatory and you also describe all of them very well.
Okay, thank you so much. Then thank you so much for the opportunity as well. I believe that I could pass some information. I think it's very simple ideas, simple things, but which we all can investigate further.
Yes, as we have now kept your recording, and I think most of the student will connect you soon.
Okay. We can discuss further details regarding this one even.
So I'll share your. We can do one thing where I'll share your email ID with them. If they have any further associated question or query, they can ask you.
Thank you so much. Okay. Then thank you so much, Dr. Rohit, and all the participants. See you all again, maybe later time. Thank you so much. Then I'm
Thank you very much. Thank you very much.
Thank you so much. Yeah. Thank you, sir. Thank you.
Hope to connect to you soon. Thanks.
Thanks.
Thanks. Okay. So, dear participants, this concludes all the sessions of this STC. And I can see your responses here. All these responses are open to me, and we are receiving very good responses here. So we are also